Let's look at another type of probability distribution for discrete data called a binomial distribution. Now, the word binomial in previous math classes may mean to you a collection of two different types of terms, maybe something like 2x plus 3y squared. And binomial does have that definition, but here it has a different definition. Its definition is that for any trial or any experiment, you only have two outcomes. Either you have a success or you have a failure. This is also called a Bernoulli trial. When you're trying to identify a distribution, a probability distribution, as being binomial, you look for some criteria. Some of those other criteria, along with success or failure, include recognizing that every trial is independent of the other trials, so its outcome does not depend on a previous event's outcome. Every trial has to be identical to the other trials, okay? So there's no changing the circumstances from one trial to the next. And we define the random variable x as being the number of successful trials. So let's look at an example. Let's say that you define success, or you define the random variable x as being rolling a 5 on a die. Okay? So if that is success, that would mean that failure, or the probability of failure, would not be rolling a die. So the probability of getting a 5, of course, would be 1 out of 6, because you've got 6 sides to the die, and therefore the probability of not getting a 5 would therefore be 5 out of 6. And that would be just for a single roll. What if you wanted to roll the die twice, and you wanted to get one success? There's a couple of ways that you could do that. The way you could get a 5 is maybe you get it on the first try. Maybe you get your 1 out of 6 and the second trial ends up being a failure. In other words, the probability of not getting that 5 is 5 out of 6. And so that would mean that the probability of getting 1 5 from 2 rolls would be the multiplication of these two, or 5 out of 36. But there's another way this could happen too. Your probability of getting 1 5 from 2 rolls could happen on the second roll and not on the first one. So it could be 5 out of 6 times 1 out of 6. But notice that the overall probability for those 2 rolls doesn't change. It still comes out to 5 out of 36. So overall, if I want to get the probability for both these scenarios, I can say the probability of getting a 5 on 2 rolls could be 5 out of 36 for scenario number 1, or it could be 5 out of 36 for scenario number 2. That means that I have 2 times 5 out of 36. But another way I could look at this as well is I could view this as a combination, which was multiplied by the probability of success, which was 1 out of 6, times the probability of 1 failure, which was 5 out of 6. And this is a great way of trying to understand where the probability formula for a binomial distribution comes from. It looks like this. Probability of getting a certain value of x is equal to, and I'm going to put some letters in here and we'll talk about what they are in just a moment. Okay, it looks like this. Okay, so n is your number of trials in your experiment. Here we only had 2 trials. We only rolled the die once and again for a total of 2. X is your number of successes, and we define that up here. So P then is your probability of success, raised to the exponent x, raised to the exponent of the number of successes, and Q is the probability of failure. So as long as we know all 4 of these variables for a given experiment or a group of trials, we can calculate the probability of getting a particular value of x. or a particular number of successes. Let's look at some other examples. Let's say that you toss a coin 15 times, one trial after another. You can recognize that all those trials are identical and that there's only two possible outcomes. You get a head or you get a tail. Okay, so this qualifies as a binomial distribution. And also the outcome of one coin flip does not depend on the outcome of the coin flip that preceded or follows it. So if you toss a coin 15 times, what's the probability you'll get exactly 10 heads? So this is example number 1 in your note. Let's begin by defining all of the variables that we need. We have the number of trials, the probability of success, which is P, probability of failure, which is Q, and the number of successes. So if we toss the coin 15 times, that means that the number of trials is 15. What's the probability we'll get exactly 10 heads? Well, we're going to deem that a head is a success. So there are 10 of them. Okay. Now, what is the probability of that success? Well, the probability for a coin, of course, is just 1/2. Right? 1 out of 2. And the probability of failure is also 1/2, but I also want to show it to you a different way. The probability of failure is always going to be 1 minus P, or the probability of success. So in this case, that still becomes 1 minus 1/2, or the probability of failure is 1/2. Let's plug these values into our new binomial equation for probability and see what happens. So the probability when x is 10, or when we had 10 successful events, or we get exactly 10 heads, is equal to 15 trials, choose 10 successes. Then times our probability of success, which is 1/2, raised to the number of successes, which is x. X is 10. So 1/2 to the 10th. And our probability of failure, which is 1/2, raised to the number of overall trials that we had minus the successes, right? So the remainder that weren't successful from these trials had to be failures. And so we can put this as 15 minus 10. I just realized in the previous slide I might have forgotten to put the exponents in to the general equation. Okay, so you can go back and double check that, but I wanted to explain to you where they come from. I was getting a little ahead of myself there. Okay, so we can go back and we can calculate these. 15 choose 10 you can just keep here on paper as such because you can allow your calculator to do it. 1/2 to the 10th means you have to put in 1 divided by 2, and then you have to use your x to the y button, or it may be similar to that, to make sure it gets multiplied by itself 10 times, or so that there are 10 1/2s. Another way of thinking of it is you can have 1 to the 10th over 2 to the 10th. Okay, that does the exact same thing. And then 1/2 raised to the 5th, again would be 1 to the 5th over 2 to the 5th. Continuing on, you can do this all in your calculator at once if you like, and you should end up in decimal form with approximately 0.09164, or if you want to change it to a percent, you can multiply it by 100 and you can get 9.2%. Okay, so the probability, again, of getting ahead 10 times out of 15 is 9.2%. Let's try another example. This time, let's go back to rolling 2 dice. They're rolled 20 times, and we'll do a couple of scenarios. Okay, so the first scenario is what happens if we get a 7, and what's the probability of doing that 8 times? So again, let's begin by filling in all of our variables. I'm going to take away the colors this time. How many trials are there? Well, it says the 2 dice are rolled 20 times, so there we are. Success is rolling a 7. We want to roll a 7 8 times, which means there are 8 successes. What is the probability of rolling a sum of 7 8 times? Well, you'll remember from the double die grid, 7s were always along this diagonal, and there were 6 of them out of 36. It's all right with you. I'm going to reduce 6 out of 36 to being 1/6 instead. If you want to put here that it was 6 out of 36, you remember where that comes from? You most certainly can. Probability of failures is equal to 1 minus p. So 1 minus 1/6, which means it would be 5/6. All right, let's put it into the probability formula. So the probability of getting 8 successful rolls, okay, where the sum was 7, is equal to 20 trials, choose 8 successes. Our probability of success, which is 1/6, raised to the number of successes we have, which is 8. Our probability of failure, which is 5/6, raised to the number of failures. If there were 20 trials, 8 were successful, that means that 12 of them were not. And you can put in 20 minus 8 here. I'm just going to go straight and put a 12. Again, you can let your calculator do the work. Try it. You should end up in decimal form with something that looks like this. And if you want to change it to a percent, you can by multiplying by 100. It comes out to 0.84%. So again, this is the probability of rolling a 7 8 times out of 20 when you throw 2 die. Okay, it's pretty low. Let's look at part B of this question. It says, what is the probability of rolling a sum of 7 out of 20 trials at least twice? So, we still have 20 trials. We still have a 1/6 chance of rolling a 7 when we roll a pair of die. And we still have a failure probability of 5/6. But down here, we're looking at a whole bunch of scenarios. We want to know what's the chance of getting a 7 at least twice. So we have to have 2 successes, but we could also end up with all 20 of them being successes, and we want to look at every scenario in between. Now that's an awful lot of scenarios to consider individually, right? Probably when x equals 2 and 3 and 4 and all the way up to 20. So this time, the probability of getting a success when it's greater than or equal to 2 could actually be done indirectly. What if we took all of the probability, 100%, let's take away the cases we don't want so we can be left with the ones we do. The only scenario that isn't included is having 1 success. Otherwise, 2 successes through to 20 successes inclusive is included here. So let's subtract the probability when we only have 1 success. Okay? Sorry, less than or equal to 1 success. Now, that includes 2 scenarios. We could actually have where we have no successes. We could also have where we have 1 success. So we need to be mindful of both of those. So we have 1 minus, again, our 20 trials. This time we have no successes. Our probability of success is still a 6th, but we have no successes. We have 5/6 probability of failure. All 20 of them are failures. From that, we're also going to subtract, I'm just running out of room, I'm going to go down here. 20 trials with only 1 success. Our probability of success is still a 6 with 1 success, and 5/6 probability of failure, and that's going to occur 19 times. All right. When you do work all of this out using your calculator, you should end up with a decimal of 0.870, which as a percentage comes out to 87%. Now this makes sense. I mean, your chances of having 2 to 20 successes is almost perfect, right? It almost includes every scenario, which isn't surprising then that your percentage is pretty high. All right, let's continue on with a couple more examples for binomial distributions. This time we're going to introduce something called the expected value, and we'll do it with a couple of scenarios as well. So in the example we just finished, what if we add a little bit of a wager to it? What if we have 20 trials of rolling a pair of die, and you're going to get paid out $7 every time you roll that sum of 7. Is it a fair game if you put $25 into play? All right, now as soon as you see the words fair game, you know that expected value is involved from our previous video. So let's remember again, the probability of success of rolling that sum of 7 is a sixth. We can find the expected value really easily. This is very similar to what we did in the first video. Our expected value is going to be equal to the number of trials times the probability of success. We have 20 trials. Probability of success is a sixth, so we end up with 20 over 6, which reduces down to 10 over 3. Okay, so that's the expected value. If we put, of getting that roll of 7, okay, with 20 different trials, let's figure what the winnings would be in that scenario. So our winnings are equal to 10 over 3, or a value of 10 over 3, times $7 every time that happens. So that comes out to $23.33. But your cost to play the game was $25. So on average, you would have a best chance at making $23.33, but you paid $25 to get in. So since these are not equal, the person who has this game has the advantage, right? You're putting in more than you could possibly win back out. So is this a fair game? No, it is not a fair game. And the expected value, or the one that we think should come up the most, helps us in determining whether it's fair or not. All right, one more example. This time you have a multiple choice question. It has 5 questions and each one of them has 4 answers, so A, B, C, and D. What's the probability that you pass? Okay, so let's look at, first of all, how many trials are there? Well, in this case, each one of those multiple choice questions could be thought of as a trial, so there are 5 of them. Okay. What's the probability of getting each one of those questions right? Well, if there are 4 answers, that would mean that you have a 1 in 4 chance of getting the right answer if you just guessed, and you would have a 3/4 chance of getting it wrong, or 1 minus a quarter. Now, if you're going to pass a 5-question quiz, you have to get more than 2.5, and since it's not possible to get 2.5 questions, a pass will mean that you have to have at least 3 successful events, or in this case, 3 questions right. So, what is the probability for us to have x being greater than or equal to 3? Well, it's going to be the sum of the probability when x is 3, when x is 4, and when x is 5. Right? 3 right, 4 right, or all 5 right would all constitute passing a 5-question multiple choice question. All right. So using our formula, 5 questions, we're going to choose 3 successes. Each success has a probability of a quarter, and there are 3 of them. Each failure has a probability of 3/4, and there would be 2 of them in this case. 3 successes, 2 failures adds up to 5. Let's look at the next scenario. 5 questions, we get 4 right, 4 successes. Still a quarter for the probability of success, but this time there are 4 of them. 3/4 chance of getting it wrong, but only 1 would become wrong. I'm going to wrap around here. This time there are 5 questions. You get them all. You get 5 of them right. You have a 1/4 chance of success, and all 5 of them are right. They all happen. 3/4 chance of not getting them right, but none of those happen. All right. It's a little bit of work to put in your calculator, but you can do it. You can do it all in one step. And if you do it correctly, you should try this. You should end up with 0.104, which you can change to a percent by multiplying by 100, about 10.4%. Okay, 10.4% chance of passing this multiple choice question if you just randomly guess. That's pretty low. All right. How many questions do you expect to get right if you go in and you're just randomly guessing? Let's calculate the expected value. The expected value for this scenario is equal to the number of trials times the probability of success. There are 5 questions. Each one of them has a probability of success of 1/4. That comes out to 5/4, or if you want to think of it this way, 1.25 questions correct if you randomly guess. Okay, this is not the percentage, this expected value. This is the value of X that you expect to be the most common response if you did this over and over again. Now this looks kind of funny to get 1.25 questions right. Maybe you think of it as being, if you don't want it to be a decimal, could we put this into the next sort of highest ratio that has integer values? So maybe you could think of it as something like this. You could think of it as 1.25 out of 5. Or maybe you think of 1.25 as being 5/4. Now I know dividing a fraction by another number looks kind of funny, but what if we say multiply top and bottom each by 4 to get rid of this denominator? A better analogy to this is instead of getting 1.5 questions right on a 5-mark question or a 5 question multiple choice quiz, you get 5 out of 20 instead, and that would be right. So random guessing, probabilities don't work so well for you. Okay, you're not going to pass if you just random guess most times. All right, so binomial distributions. You've got the criteria for recognizing them. You've got some equations to find probability. The biggest thing with this one is you want to set up your variables first before you go ahead and do the math, and it just makes the subbing into the equation so much easier. All right, enjoy your practice. Let me know if you have any questions.